In the 1980s, India set out to build a fully indigenous power plant for its frontline fighter, the Tajis. The Cavari engine was supposed to be the heart of India's air superiority, but the project hit a wall. The engine was heavy, and it couldn't generate the massive thrust-to-weight ratio required for supersonic combat maneuvers. By 2008, the government faced a choice between the engine and the aircraft. They chose the aircraft, officially delinking the Kaveri from the Tajis program. The public narrative settled quickly. The Cavari was a $239 million sunk cost and a 40-year failure in aerospace engineering. Yet, while that narrative took hold, the engine didn't disappear. It is undergoing final high-altitude flight trials in Russia, racing toward a 2026 certification deadline. Why is the Ministry of Defense aggressively funding and setting strict mandates for a project the rest of the world has already written off? India treated that $239 million as an expensive tuition fee. To put that budget in perspective, Western aerospace giants have spent billions of dollars and decades of iterative research to master the physics of jet propulsion. That investment bought India propulsion literacy, the baseline testing labs, domestic supply chains, and engineering protocols required to build anything that flies. That literacy is now paying out in 3 specific ways: stealth drone power plants, marine turbines for the Navy, and leverage in international technology transfers. Today, we are auditing the exact return on investment India is extracting from the Cavari program. This chart shows the shift. India moved away from trying to force the Cavari into a supersonic fighter and focused instead on the 2026 reality, powering the Godic uncrrewed combat drone. Designers repurposed the core technology by removing the entire afterburner module from the original engine. This created the dry Cavari, a derivative that produces a steady 49 kilonewtons of thrust. Stripping the afterburner means the engine can no longer provide the supersonic bursts needed for a dogfighter, but it is exactly what's needed for the Godic, India's 13-ton stealth drone designed for long-range, deep penetration missions. This thermal map shows why. A non-afterburning engine produces a much smaller, cool exhaust signature. That lower heat profile makes the drone nearly invisible to enemy infrared sensors and helps it evade long-range radar detection. This configuration provides a stable, high subsonic cruise, allowing the drone to stay in the air longer for precision strikes. The lack of high-end thrust that disqualified the Cavari from dogfighting is precisely what makes it the optimal choice for a stealth platform. To keep the program on track, the Ministry of Defense mandated that the engine must be certified by 2026, synchronizing its readiness with the drone's airframe. Because India lacks domestic high-altitude testing facilities, the team is using the Groma Flight Research Institute in Russia to validate the engine's reliability. The dry Cavari is currently integrated into this Ilyushin IL-76 flying testbed for its final flight evaluations. Testing involves pushing the engine to 43,000 feet for 75 hours aloft, simulating the thin air and extreme temperatures of high-altitude flight. This real-world data collection is what finally brings the engine to a technology readiness level of 6. Surviving these high-altitude flight trials is the final major hurdle before the Godic stealth drone can move into mass production. However, India still has a gap to fill. Its future 5th-generation fighter requires a massive 110 to 130 kilonewtons of thrust to reach full capability. The dry Cavari architecture physically cannot scale up to meet the requirements of a manned supersonic fighter. To solve this, India entered a $7 billion joint venture with Francis Saffron to build a clean sheet engine from the ground up. India secured 100% intellectual property rights and full technology transfer as part of this deal. The focus of this transfer is hot section metallurgy, the most guarded secret in aerospace. This includes the single crystal turbine blades that must operate at temperatures higher than their own melting point without deforming. Controlling this IP ends India's dependence on foreign suppliers, removing the risk that future sanctions could ground its fighter fleet. The knowledge gained from 40 years of Kaveri research gave India the technical expertise required to negotiate this full transfer from France. We can now finalize the ROI audit for the Kaveri program. First, uncrrewed propulsion. The engine is now the primary power plant for India's stealth drone fleet. Second, marine power. The project delivered 12-megawatt turbines currently being used on naval vessels. Third, industrial base. Domestic manufacturing majors like Godridge and L&T are now part of a certified aerospace supply chain. And finally, 5th-generation fighter propulsion. This remains a deliberate no. That no is actually a sign of progress. It shows India has the industrial maturity to delegate fighter propulsion to the Saffron partnership while focusing its own hardware where it actually works. India's future roadmap for the Cavari technology is now clearly defined. This engine family is suited for uncrewed platforms and naval ships, where its weight isn't a critical mission penalty. But the hardware should not be used for future manned supersonic fighters. India is moving away from experimental research and into active aerospace production. By focusing the Cavari on drones and partnering with France for fighters, India stopped trying to force the hardware to perform tasks it wasn't designed for, securing the technology needed to control its own airspace.